one of the most important reactions that alcohols are involved in are oxidation and reduction reactions, as we'll see later in the chapter. But in order to discuss those, we have to understand what they are, and they're based on something called oxidation states. Now, in general chemistry, that's usually just passed off as the charge on an atom. But it's a little bit more complicated than that. In Organic Chemistry 1, we learned about something called formal charge, and now we have to come to terms with oxidation states. Now, they both are describing charges on an atom, but they're often different things. So let's clarify our thinking about those two concepts so that we can recognize oxidation and reduction more easily and discuss those types of reactions more clearly. Okay, in general chemistry, you were first introduced to compounds as bonds as either being covalent or ionic. And the truth is those are the opposite ends of a spectrum, but they are connected. A bond is completely covalent if the electrons in the bond are shared perfectly between the atoms. So for example, if you had two hydrogen atoms, the electrons in between them are shared perfectly because they're not more attracted to one hydrogen atom than they are to the other. So that would be completely covalent. On the other hand, something that was completely ionic, that's where the differences in electronegativity were so big that only one of the atoms ever had the electrons at any given time. So for example, if you had sodium and fluorine is so much more electronegative than sodium that it just steals the electrons from it, and it doesn't share them at all in any way. Now those are extreme cases. Most of the bonds that we see, especially in organic chemistry, lie somewhere in between. Electrons do share, or atoms do share electrons, but they don't share them evenly. So for example, in water, these electrons in these bonds are being shared, but the electrons are slightly more attracted to the oxygen. So the oxygen's slightly negative, and the hydrogens are slightly positive. So you get these partial charges. You'll notice you have the bond, like in a completely covalent bond, but you also have the charges, like in an ionic bond. So these exist somewhere in between covalent and ionic bonds. And they're most of the bonds that we deal with in organic chemistry are these polar covalent bonds that are in this in-between region. Now, when we want to think about the charge on an atom all by itself, it's a little tricky because these electrons are really around two atoms, and where they are on this spectrum is not always completely clear. So when we're sort of doing bookkeeping and trying to keep track of the electrons around an individual atom, we can make a simplifying assumption. We can either assume that all the bonds around the atom are completely covalent, or we can assume that all the bonds around the atom are completely ionic. It's from those two assumptions that you get formal charge and oxidation state. If you assume, and it's often not true, it's just a simplifying assumption. If you assume that all the bonds are covalent, then the charge that you calculate is called the formal charge. We learned how to calculate that in Organic Chemistry 1. And if you're interested, I'd be happy to send you videos to review for that. If you assume that all of the bonds are ionic, no matter how slight the difference is between the electronegativity of the atoms, if you just assume they're completely ionic, then you end up getting a different charge around the atom, and that's called the oxidation state. So these two ways of keeping track of electrons, these two ways of simplifying your view of bonds to keep track of the electrons around an atom, leads to two slightly different charges on the atom, the formal charge and the oxidation state. And we can illustrate how those are different. I want to illustrate how they're different with a few different compounds, 5 of them. Okay, formal charge. Let's take methane. We're going to assume that all of the bonds here are completely 100% covalent. And what that means is that in each of those bonds, one electron will be on the hydrogen and one will be on the carbon for each of those bonds. Now when you compare that with the number of bonds normally around carbon, number of valence electrons normally around it, carbon is in group 4a, so it normally has 4 valence electrons. Then you subtract the number of valence electrons around it here, that's 4, and the formal charge is 0. Compare that with what happens when you think about this, when instead of assuming that all the bonds are perfectly covalent, you assume that they are perfectly ionic. Now, carbon is ever so slightly more electronegative than hydrogen is. Not by, by very, very little, but by a tiny, tiny amount. So if you use that difference in electronegativity and you assume that because of that, it gets all of the electrons in the bond, then we're going to calculate a very different charge on that carbon. The charge on this carbon is going to be the oxidation state. Now, carbon normally has 4 valence electrons around it because it's in group 4a on the periodic table. Here, it has 8 valence electrons around it, and so the oxidation state for that carbon is -4. So notice how different that is from the formal charge. Okay, I know it's a little strange, so let's practice this a little bit more. We'll do this with methanol now. Okay. So for the formal charge, we're going to assume that each of those bonds is 100% perfectly covalent. So for each bond, I'm just going to replace it. 1 electron will go on each of the atoms in the bond. And notice this carbon has 4 electrons around it. So carbon is in group 4a, it would normally have 4 electrons around it. Here it has 4 electrons around it. And so the formal charge here is 0 again. But notice what happens when we try to calculate the oxidation state. We know that carbon is ever so slightly more electronegative than hydrogen, so for each of those bonds, the carbon will get the 2 electrons in the bond, if we assume that it's perfectly ionic. But the oxygen is more electronegative than the carbon, and so the 2 electrons in that bond will go onto the oxygen. So now if we look at the carbon and we think about the oxidation state, we'll take the number of electrons normally around carbon, that's 4, and we'll subtract the number of electrons around it here, which is 6. And that gives us -2. So there's a -2 oxidation state on the carbon there. And notice again, the oxidation state is very different from the formal charge. These are 2 ways of, the true charge around the carbon is somewhere in between these, right? These are 2 extremes. This is assuming perfect covalence. This is assuming perfectly ionic bonds. And the truth is somewhere in between. But these are the extremes. And those margins define the center. Okay, so let's try to do this now with this next molecule. This is formaldehyde. Okay, so for the formal charge on the left, we're going to assume that all these bonds are perfectly covalent. So every time I erase a bond, I'm going to put 1 electron on each of the atoms that were in the bond. Now if we look at this carbon, we'll say, okay, carbon is in group 4a, minus here there are 4 electrons around it, and so the formal charge on that carbon will be 0. The oxidation state, though, for that, we assume that all the bonds are perfectly ionic. Now, carbon is more electronegative than hydrogen, so each of the bonds to hydrogen will become lone pairs on the carbon. Oxygen is more electronegative than carbon, And so each of the bonds to oxygen will go completely. The electrons in those bonds will go completely on the oxygen. And so here is our carbon. We know carbon is in group 4a. It normally has 4 valence electrons around it. If we assume that all of those bonds are perfectly ionic, it would have 4 electrons around it. And so the oxidation state here is 0. So notice that the oxidation state can sometimes be, the same as the formal charge. And that means that the charge on this carbon is close to 0. So we have that electronic bookkeeping there. Okay, now we can do this with these other two molecules. Let me skip ahead just to carbon dioxide. We'll just try it with this last one, and then we'll dive into exercise 1319 to show how this understanding of oxidation states will help us recognize oxidation and reduction. Okay, so if we have the formal charge, then we'll assume that all the electrons in those bonds are evenly shared. 1 electron goes on each of those atoms in the bond. And so the formal charge for carbon in carbon dioxide, carbon is in group 4a. It normally has 4 valence electrons around it. Here it has 4 valence electrons around it, if we assume that all the bonds are perfectly covalent. And so the charge on this, the formal charge on this, would be 0. If we think about the oxidation state on the carbon, then we'd assume that all these bonds are perfectly ionic, and the electrons in the bonds would go on the more electronegative atom exclusively, and those are the oxygens. So if we look at the carbon here, carbon normally has 4 valence electrons around it. It doesn't have any here, and so it would have a positive 4 oxidation state. Okay, and so again we see that the formal charge and the oxidation state are very different. The oxidation state changes as you get more electronegative atoms bonded to an atom, because it changes where the electrons in the bonds are going. Oxidation is defined as when the oxidation state of an atom becomes more positive, and reduction is when the oxidation state of an atom becomes more negative. And so with every bond to an electronegative atom, the carbon that's bonded to it will lose electrons and become more positive. So effectively, what happens is the more bonds to electronegative atoms there are, the more oxidized the carbon is. So in exercise 1319, it says, in each of the following transformations, identify whether the starting material has been oxidized, reduced, or neither. And try to determine the answer without calculating oxidation states, and then use the calculations to see if your intuition was correct. Okay, so without doing any calculations, notice there are 2 bonds to an electronegative atom here. There are also 2 bonds to an electronegative atom here. The number of bonds to an electronegative atom didn't change, and so the hypothesis would be that this would neither be oxidized nor reduced. If the number of bonds to electronegative atoms increases, then the electrons are getting stolen from the carbon. The carbon will have a more positive charge, and so it'll be oxidized. If the number of bonds to electronegative atoms decreases, then the carbon starts to get the electrons. It has a negative charge, it's reduced. But if the number of bonds to an electronegative atom does not change, then the carbon atom is neither oxidized nor reduced. Now we can use the calculations for that here. If we have this carbon, and here, this carbon would lose the electrons to both of the bonds in the oxygen, So if you assume that these are perfectly ionic bonds, those electrons will both go onto the oxygen. And so just from those, we'd assume that we'd have this sort of positive 2 charge on the carbon there. And a similar thing happens here. I myself find that the calculations are a little bit cumbersome, and they make it a little bit more complicated. It's often more useful just to look at the number of bonds to electronegative atoms. Okay, so let's try to do that with a few more examples. So on the left here, we have, let me just draw this in a darker color. We have 2 bonds to an electronegative element. Those are these 2 bonds here. On those 2. That's on the left side of the arrow. On the right side of the arrow, we have 3. We have 2 going up, and then 1 going to the left. If the number of bonds to an electronegative atom increases, then this carbon is going to lose electrons. It will become more positive. And so this will be oxidized. Okay, let's try C. On the left, we have 3 bonds to electronegative atoms, 2 going to the oxygen on the top, 1 going to the oxygen on the left. So that's 3 bonds to electronegative atoms. On the right, there's only 1 bond to an electronegative atom. So the number of bonds to the electronegative atoms decreases. If the number of bonds decreases, then these atoms are not, those electronegative atoms are not there to steal the electron density away. This carbon is very positive here. It becomes more negative on the right, and so this is reduction. So if the number of bonds to electronegative atoms decreases, it's reduced. Okay, let's try D. Here we have 2 bonds to an electronegative atom going up and 1 going to the right. So we have 3 total. If on the right we have 2 bonds to an electronegative atom going up and 1 to the right. So again we have 3 total. Notice that the specific electronegative atom doesn't matter. It could be chlorine, it could be oxygen. The important thing is the number of bonds to an electronegative element. And because it doesn't change here, this is neither oxidized nor reduced. Now, for your homework assignment, just to drive, I'm going to try to bridge this. I'm not going to write everything out to make the video a little shorter. But when you submit this homework, you will want to write this type of reasoning out for each of these. Count up the number of bonds to electronegative atoms and circle them, both for the products and for the reactants. Then, say whether the number of bonds to an electronegative atom increases or decreases, and conclude whether that's oxidation or reduction. Okay, so for this next one, on the left side we only have 1 bond to an electronegative atom. On the right side we have 2. The number of bonds to electronegative atoms increases, and so that is oxidation. The carbon will lose electrons and become more positive, and so become oxidized. Okay, on the left here there are 2 bonds to electronegative elements. On the right there's 2 plus 1, that's 3 the number of bonds to electronegative elements increases, and so, again, this compound is oxidized. This carbon will lose more electrons there, become more positive, and so be oxidized. And so, you would want to write these out in complete sentences, so I'll just give you, since this is the last one, if you get the point, then you'll be able to write them out on your own, and if you just want to see an example at the end of this video, you can continue watching, and I'll write out an example of how you would want to fill this out in your homework for full credit. So you'd say, the reactant has a carbon with 2 bonds to electronegative, or I should say to an element, as circled, or here highlighted. The product has the same carbon with 3 bonds to an electronegative, or 2 electronegative elements. Or I should say atoms, really. And again, as circled. Because the number of bonds to electronegative atoms increases, the carbon becomes more positive and is oxidized. So that's an example of the type of reasoning. And if it were reduction, then you'd say because the number of bonds to electronegative atoms decreases, the carbon becomes more negative and is reduced. So hopefully this video has clarified a little bit the difference between formal charge and oxidation state. Formal charge assumes that all the bonds around an atom are covalent, and oxidation state assumes that all the bonds around an atom are ionic. And they sort of describe the extreme states of what the electrons could be like around the atom. Most of the bonds that we deal with will be somewhere in between. They'll be polar covalent in organic chemistry. And so we can get useful information by sort of looking at them in 2 different perspectives, the perspective of the formal charge and the perspective of the oxidation state. As we'll see, for alcohols, the oxidation state ends up being a really useful measure. It tells us how many bonds to an electronegative element we have. For alcohols, that electronegative element is going to be oxygen.